it's got, you know, like a line over here that looks like just one wire, but it's really two wires. Right? And I can just separate them even further. But then one of those connects to one terminal. There's a light bulb. Another one. I hope I don't lose the connection there. And if I turn this crank, I can make electricity. You know, I'm just turning. I don't know if in this unit, I haven't actually seen the inside of it, but I don't know if in this unit there's a coil spinning in the presence of a magnet that's stationary, or the magnet is, or the coil is stationary, and then this spins the magnet. Right? And it doesn't matter if I turn it one way or the other way. You'll notice that the faster I turn it, the greater is going to be the change in the magnetic flux, and therefore the greater is going to be the voltage induced, and therefore the greater is going to be the current. And the light bulb is going to glow brighter. If I just barely do it. Making electricity, in this case, this is a generator, right? You're putting in mechanical energy. And that mechanical energy is getting converted to electrical energy. And in the motor, you have the electrical energy getting converted to mechanical energy, so something moves, something goes. But that's the idea. You can play with that if you like at the end of class. So, yeah, we're going to do this lab here. The first part of the lab, you'll notice, deals with, you have a coil, and I'm going to give you a coil, and then we're going to connect a galvanometer at the ends of that coil, which is just, it's like an ammeter. And then I'll give you a bar magnet, the ones that you used to measure the magnetic field last week, you know, for various distances along the axis and so on, away from the center of the magnet. So then you're gonna grab the magnet, let's say with the north end moving closer and closer and closer to the coil. And then as you do that, then you'll write down what you observe on the galvanometer. Oh, I see a deflection to the right. It's half scale, full scale. And then you're going to leave the magnet there, and then what do you observe? And you should observe nothing. The galvanometer needle reads 0 current. And then when you put it out, then the deflection should be the other way, because the induced current is going to be the other way, right? Because now you're decreasing the flux. If the current in the coil is one way, when you increase the magnetic flux through the coil, it'll be in the opposite direction when you decrease the magnetic flux through the coil. So that is just Faraday's law. So you just do something, and then you observe something, and then you write that down. And then you leave it there, and then you write something down. And pull it out, and then you write something down. It'll be like that. And then at the end, you build the transformer, and you make measurements, and you pretty much test, you know, the efficiency of the transformer. Test this equation using your cheap transformer. But nevertheless, you'll get the picture. It's kind of nice because you get to see it.
So are the transformers that are at power plants able to channel all of the magnetic field that you're talking about with the iron?
I would say not all, but you know, a lot of it. You know, better than the ones that, you know, better than the factor that we're gonna get.
Gotcha.
Yeah. They tend to be closer, and yeah, they've learned various ways to maximize the transfer flux. Okay. But somehow So this is chapter 29. Oh, you get to see this, right? And I posted today in Coral an assignment on chapter 27. So, work on that. If there are issues, which it seems like there always are issues, let me know so that then they can fix it and we can move along. But work on those. But there are a couple of nice problems in there. But remember, focus also. I mean, those you gotta do because they're for credit, right? But don't forget the problems for which I wrote down solutions and that I posted on the website for the course. Okay? So, those suggested problems, they're kind of nice too. So, induced electric fields. I want to do a calculation on induced electric fields. Let's look at this particular problem or situation. So this is a lot better than what I can do on the board trying to draw this thing. So just imagine that you have a solenoid. That's the coil, right? With many turns, right? This is not a transformer. This is just, transformer is just an application. This is just something else. It's related to it, but you have this coil, right? And suppose the current in this coil is down this way. You can see it, right? This way. The current is, and then it goes back out in the front, goes down the front, back out in the front, down into, back out. So the coil, the current is like this, and then goes at the back, it goes out, to whatever the source is, right? It doesn't matter what's producing this current, but it's just, there's some source of voltage over there that, sets up this current in this coil. Now, since the current in this, just think of it as a solenoid, right? The current is like this in the solenoid, it produces a magnetic field indicated by this direction, this blue arrow. So this solenoid has current out this way, into the base this way. Just curl your four fingers in the direction of the current in the solenoid, and then the magnetic field is this way, right? Now, if this current is constant, that would be magnetostatics. Then we get that the magnetic field is mu naught N I, where N is the number of turns per length in the solenoid, right? If it's a very long solenoid. And the magnetic field will be constant if the current in the coil is constant, right? Now, what would happen if the current in this wire that comes in, connects to the solenoid, what happens if that current is changing? What if it gets bigger and bigger and bigger? In other words, what if this current in this solenoid over here is increasing? If the current is increasing, right? If the current is increasing, then this magnetic field gets bigger, 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 bigger. And if I put a ring over here, if I put a ring over there, right? Then as far as this ring in blue over here, metal ring in blue is concerned, it's got a flux going through it due to this magnetic field that the solenoid produces. And from the point of view of this ring over here, if this current in this solenoid is getting bigger, 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 then this magnetic field is going to get bigger, 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 and then the ring is going to say, no, I want that flux to stay the same. So therefore, this ring will have an induced current in this direction, right? Like that. So that it produces its own magnetic field in the opposite direction to the one set up by the solenoid to keep the magnetic flux constant. It's opposing the change in the flux, right? Like Faraday's law. So then, while this current in the solenoid is increasing, there will be a current in this ring. And that ring over here doesn't have a battery connected to it. In fact, it could just be a ring like this. Now, if there is a current established in this ring over here, what did we say establishes a current in a wire when we were in chapter 25, 26? When we were considering those circuits with batteries and resistors, and we said, oh, the current is this way, right? Essentially, that's because there was an electric field set up in those wires, right, by the battery, by the DC battery. In this case, you don't have a battery connected to this ring. Yet, there is a current. And remember that if the current is said to be in this direction, in this ring, that's because there must be an electric field in that direction that actually makes the electrons in this ring over here go the other way. Since the electrons go the other way, we say the current is this way. But let's just think of the current being I prime in the ring, right, being this way, down behind them comes up over here. If the current is that way, then there must be an electric field in that wire that causes those electrons to move actually in the opposite direction to what we say is the current, right? And the question is, what is the strength of that electric field? And what is the source of that electric field? So Faraday's law can be written like this. What we wrote was this. We said that the induced voltage, which is the EMF, that's how we wrote it, right, is minus the derivative with respect to time of the magnetic flux, right? This is how do you write mathematically Faraday's law. Now, and we talked about an induced current, and the way that we were able to quantify that induced current was by saying that the induced current in the ring, for example, would be this voltage that's induced in the ring divided by the resistance of the ring. Or this is just EMF divided by R, right? So we use Ohm's law to quantify the current in the ring. Now, how do we calculate the induced electric field in that ring, resulting from the change in magnetic flux through the ring? Do you remember that at some point we wrote down an expression like this? dV is minus EdR, and we did, or dL. So Faraday then wrote this expression that this is also equal to the electric field started with a length along the ring, and then you do this and you write it like that. So this is the induced electric field. So this circle over here just means it's along that loop where the induced current was established. And this electric field that's induced, it's induced in the direction of the induced current, which we know how to calculate using Lenz's law. So if you want to know what is the direction of the induced electric field, well, it's the same direction as the induced current, which is just use Lenz's law like we did last week. Now, what's interesting here is that this electric field is not just induced in this coil, in this ring over here, but it's induced in the space, all of this space over here. It's just that, like the electric field that's induced over here, right? There are no electrons over there to flow so that there's no current, right? But it is induced in this space. And if you want to know what is the magnitude of that induced electric field in this ring, in this particular problem, it is good, or it's convenient to take the point of view as if you're looking down this solenoid over here, and you look at the ring, and it's going to look like this. right? It's gonna look like this. So here's the magnetic, if you put your eye over here and you look that way, A is the area of this ring. Let's just call it A, right? The magnetic field is into the page, so those are these X's. This is the magnetic field going into the page. That's the external one, right? Produced by the current in the solenoid. The ring is like this. The current in the solenoid, right? So notice it goes like this, it goes in the back, comes in the front to the right. So the current is in the clockwise direction. So this I over here is the current around the solenoid. This blue region over here is the area of the solenoid, and the ring is further out. There's a space over here with vacuum from the solenoid to the ring. But because this magnetic field is getting bigger, 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 this ring over here has an electric current in this direction to produce a magnetic field out of the board to counteract this one, to oppose the change in the flux. And since the induced current is this way, counterclockwise, as seen in this picture, that means that the induced electric field is also that way. So if you use this formula, this is Faraday's law in integral form, you can easily calculate the magnitude of that electric field. Because if you just write down the integral like this, around that ring, induced equals minus ddt of the magnetic flux through it. This just becomes E, right? The electric field is along the ring, and then you multiply by the length of the ring around, which is 2 pi r, it's a circle. And this is minus ddt. And what is the magnetic flux through this ring? Well, the magnetic flux is the magnetic field times the area, but this magnetic field extends only up to the blue edge over here, because the magnetic field is confined to the inside of the solenoid. So it would be the magnetic field inside the solenoid, right? Produced by the current in the solenoid, times what is the area of that would be area A. Let's say that the radius of the solenoid is A, not this R. So this would be pi A squared. So this A is the radius of the solenoid. Now, what is the magnetic field inside the solenoid? That's mu naught times the number of turns per unit length in the solenoid multiplied by the current in the solenoid. Not? Yes? If you remember, mu naught and I is, by Ampere's law, we were able to derive the expression for the magnetic field inside a solenoid. So you're right that the magnitude of the induced electric field times 2 pi r, where r is the radius of that ring, that distance r from the center of that solenoid, is minus ddt of, and then we have mu naught, the number of turns per unit length of the solenoid, pi, well, I'll write down the I, pi a squared. Which of all of these quantities is changing with time?
Current.
What's that? The current. I, right? We said that the current is increasing. If the current is increasing, the current is the one that's changing with time. So this derivative only acts on the current. This guy only acts on the current, right? So therefore you have E induced times 2 pi r equals, the minus sign is really there to tell us something about the direction of that induced electric field, but I find the direction, I figure out the direction of the induced electric field by figuring out the direction of the induced current, right? And I use Lenz's law for that. So I'll copy it down, but then by law, what direction that's going to be. So I have a mu naught, an n, a pi, an a squared, and then the I dt, the rate at which the current is changing. And then this pi cancels that pi, and therefore I can write that the induced electric field, what I would do in a problem like this, given that the current is increasing in the solenoid, so for this particular problem, the magnitude of the induced electric field would be mu naught A squared. Oh, there's also an N over there, right? I have a 2R and a di dt. And in that picture, counterclockwise. I'll just leave the minus sign out because that's really there to tell me something about the direction, and from that diagram over here, it would be in the direction of the induced current, which is counterclockwise by Lenz's law. So notice that we have this R dependence. The further away you are from the solenoid, the weaker the induced electric field is going to be. Essentially, what's happening over here, the physics in general here is this. There is an induced electric field because there is a change in magnetic flux through the ring. But what's changing through the ring, what causes that change in that magnetic flux is the fact that the magnetic field is changing, right? So because the magnetic field through the ring is changing, there is induced an electric field. So Faraday discovered Faraday's law, and one of the statements of Faraday's law is that whenever a magnetic field is changing as time goes on, whenever a magnetic field over some region of space is changing as time goes on, there is associated with that change the appearance of an electric field. So time changing magnetic field is associated with the appearance of an electric field. So it's like Faraday taught us that a time changing magnetic field gives rise to an electric field, an induced electric field. So that's a neat problem. What if I asked you, what is the induced electric field like right there? At a distance r from the center that's smaller than the radius of the solenoid. I'm not interested in the induced electric field over there, but outside the solenoid. But what about inside? What is the induced electric field inside? So in that case, what will change, will be the change in this calculation. If I want the induced electric field, let's say inside the solenoid as opposed to out here in this ring, what will be the change that I will need to make? Anyone? So essentially what we would do is this. Essentially what we would do is this. We would say, I need to calculate the magnetic field, the induced electric field here at a distance r from the center. So instead of thinking of this ring, you think of this ring. Right? And then you say, okay, so you write Faraday's law like this. You can write it with this E induced dotted with dl equals minus d dt of the magnetic flux. So this becomes E induced, and then integrate over that length around the ring, which is 2 pi r, equals minus d dt. Now, what is the magnetic flux? This is the magnetic flux through this ring. So I want the magnetic flux through this only. And that would be what? B times the area of that, which is pi r squared, not pi a squared. Can you see the difference? Right? What I'm changing is this. And then, the pi's cancel, and then you get that the E induced. And if the magnetic, and same thing over here, this is still mu naught and I, so this would be minus 1/2 pi, and this would be mu naught n r squared times di dt. And then I forgot an r, right, downstairs. So this is gonna cancel that. I also cancel the pi, right? I meant to write 2r, not 2 pi. And then again, if the current is increasing, then the induced electric field will be that. Because that would be the direction of the induced current as the current in the solenoid is increasing, right? Because if the current in the solenoid going like this is getting a bigger magnetic field this way, then in this ring you would have an induced current this way, so that it produces a magnetic field to oppose the change. Now, there wouldn't be a current in here because there's no wire in there. But there will still be an electric field induced over there. It's just that, the electric field will be there, but there are no electrons over there to then make up a current. But when that electric field is induced, it's actually induced all over the place over here. When that electric field is induced in this metal, now there are free electrons, and then those are going to run around, right, making up an induced current. But there will still be an induced electric field in the region of space. So this means that the induced electric field would have a magnitude of mu naught n over 2 the I dt, depends on how quickly the current is changing, and then you have a factor of r. But as soon as you step outside the solenoid, it's going to drop as 1 over r. So if you did a graph of the induced electric field as a function of distance, this is 0, this is r equals a. So inside the solenoid, the electric field is going to grow linearly with distance. So it'll go a straight line like this, and then it's going to drop as 1 over r. So this is outside the solenoid. It's kind of 1 over r dependence. And this expression over here would be inside the solenoid. This is growing with distance. So this is inside. Pretty good problem for a final exam, right? Again, notice the difference between, why did I put an A over here and not an R? Why did I put B times pi A squared as opposed to B times pi R squared? Why did I do that?
Because the ring was outside of the...
And, yes, and? Why not make it R? Because the electric field is induced at a distance R.
There's nothing between that, in that empty space.
Right. The magnetic field is confined to the solenoid. So the magnetic field in the blue region over here is mu naught n I. But the magnetic field between the solenoid over there, that's 0. It's like, you want this magnetic field through this area, multiplied by that area. But then this magnetic field times this area, but there's no magnetic field from the edge of the solenoid to the ring. So that doesn't contribute. There's no contribution to the magnetic flux from this region over here, because there's no magnetic field over there. Right? So that's why this is different than this. In this case, when you consider this ring over there in red, you have magnetic field all the way up to where you're calculating the induced electric field. So there is a magnetic flux all the way through this, ring that you imagine over here. Now, there wouldn't be an induced current over there because there are no electrons over there to move around. But that electric field is induced all over the place, but in this ring, right, when it appears over there, this ring, it's a metal, it has free electrons, then those are going to respond and make up a current. But the message is that you can write, if you like, this ddt over here as ddt of the integral of the magnetic flux. Oh, not like that. That's the A. That's magnetic flux, right? So essentially, what this is saying is that electric fields can be produced by a time-changing magnetic field. And more generally, by a time-changing magnetic flux. But you can associate a time-changing magnetic field with an electric field. That is what Faraday taught us. So, I guess, I'm sorry I wrote on the board because that picture is so much better than what I can do myself. This picture here with the solenoid, right, this is a lot easier to see this than if I attempt to draw that on the board over here.